This is a high school geometry lesson on similar solids and working from solid to solid. Let's remember that similar solids or similar shapes of any type are going to be the same shape and usually a different size. They will have the same aspect ratio, which means that the scale factor is true for all parts of it that are linear. And we'll talk today about a relationship between where you can use the scale factor in 2 and 3 dimensions. Okay, the first thing is that when you have a shape that's similar to another one, the sides will of course be proportional, and we'll have the scale factor, or here written as the ratio here of them. Okay, so given as a ratio, the height of one is the height of two as each of them. They're all the same for the corresponding parts, and they will reduce or simplify to the same ratio. What we can see is, as we've talked about before, that to use the scale factor in 1 dimension, you use it 1 time. To use it in 2 dimensions, you'll use it once for each dimension. For example, once for the length and once for the width. Refer back to my PowerPoint with regard to doing this. To do it in 3 dimensions, you'll use it once for the width, once for the length, and once for the height, or the cube of it. So again, in 1 dimension, the exponent of the scale factor is 1, and therefore not written. In 2 dimensions, to convert, you use the scale factor squared, 2 dimensions, exponent of 2. In 3 dimensions, you'll use the scale factor 3 times, once for length, once for width, once for height, or 3 cubed. Okay, let's look at some problems about how this would work. Okay, first off, let's look right here at number 3, and I'll work on that one. Okay, how are we going to do that? Well, we'll have, let's see, well, we need to find the ratio, the scale factor, so I'll set up my 2 by 2 chart, and I'll do radius and height will be 2 ways that I compare it, and the 2 circumstances will be solid 1 and solid 2. I'll fill in my chart, and I'm going to rehearse to myself. The radius from the first one is 7. The height from the first one is 16, because you're going to get it wrong. Not because it's hard, but because it's like way too easy. Okay? Same deal here. The radius from the second solid, the radius, the height of the second one. Reminder, the inside of our 2 by 2 chart forms our proportion. Okay. And then we can solve to see if it's true, to see whether or not these are similar. So the product of the means is the product of the extremes. So that would be 7 times 10. 7 times 10 is 70. And 70 does not equal 4 times 16, which is 64. So these are not similar. Okay. You recall that proportions are really handy. You can set them all sorts of different ways. And so let's look again here at how we can do it. I've already written out for you. You can do it 2 ways. Here I've set up my chart with 1 and 2. I kind of like it better that way. Either way works just fine. You remember our properties of proportions told us that we could do that, and we can. So now I'm setting it up in this fashion. And what I'm looking at it, because I personally kind of like to do it with scale factor. Doesn't matter, you'll get the same thing either way. They're all variations on the same theme. And so I like to think of, what do you do to 16 to get 7? Well, you multiply it by 7 over 16. The 16s will cancel, you'll get 7. When you do that, that's for the first. That gives you the aspect ratio of the first one, and then you get the second one. and you see, oops, it's not the same. Okay? So that tells us that they are not similar solids. You can also set it by proportion, which is what I just did, and you see that, again, they are not proportions. Any way you stack it, they're not proportional. Okay, so let's look at this one right here. Okay. I'm going to do the same thing. I'm going to set it up. Whichever way you want to set up the proportion is fine. This is how I chose to do it. Shape 1 and shape 2, length, width, and height. In my little in this case 2x3 chart, you can extend it in that fashion. Again, I've done the same type of calculation here, and here they're trying to catch you. The scale factor, again, what do you do to 5 to get 9? Multiply it by 9 over 5. Need over know. Need the 9. What do you do to 5 to get 9? 9 divided by 5. Need over know. When I do 7 times 9 over 5, I get 12.6, which is correct for the second dimension. And when I do 11, the third dimension, height, times 9 over 5, I get something different. And so I find that they're not proportional. Now, your tendency is going to be to say, oh, well, that worked, it's good. No, you've got to try it for each dimension. Notice that the length and the width were proportional. The base of the pyramids are similar, but the whole solid is not. This is actually too squat for this one. This one's taller and leaner, and this one's a little shorter and squat. You get the same thing when you try it over here with proportions. The first one will work when you do your product of the means as the product of the extremes, and the second one will not work. If any of them don't work, it's not a proportion. You're done. Okay, go ahead, if you would, and do the other two problems here, and pause the playback, and I'll give you the answers. Okay, here is the two rectangular prisms, the two boxes, and how I worked it out. They do turn out to be similar. And here are the two cones. Okay, now the next step is going directly from volume to volume. Now this is going to be kind of weird for you because it's going to seem wrong when you do it. It's 8 times as much, because say if it's twice as big, if the length or the linear dimension is twice as much, then the area is 4 times as much, 2 times 2, one's for length, one's for width. 8 times as much, length times width times height. So it's going to get big really fast, and it's going to look wrong until you get used to that concept. So again, we'll use the need over know to remember how to do it. If I'm going from here to here, I need this one, I know this one. So how that would work, I'll look here at the first one with the balls here. Okay. So that would be need over know. The one I'm looking to go to, I'm assuming I'm going this direction. It'll work either way. Because the reason I'm saying, the reason it's asking is it tells me to go from 1 to 2. So 2 is where I'm going to. So that'll be 125 pi is the volume of 2. And then the volume of 1 is 8 pi. The pi's cancel. I can simplify it. And that'll give me 125 over 8. To do that, I'm going to need to take the cube root, because remember, applying the scale factor going forward from small to big, it's times length times width times height, and then to undo it, it's going to be, or times the cube, it's going to be the cube root. Okay, so I'm going to want the cube root of 125 over 8, which will be the cube root of 125 over the cube root of 8, which is 5 over 2. Okay. So the scale factor from 1 to 2, ball number 1 to ball number 2, sphere number 1 to sphere number 2, is 5/2. So that means any linear dimension that you'd have in one, say for example the radius, say I have it, whatever the radius here is, that one will be 2.5 times the size of it. Okay? And any surface area that you do will be 2.5 squared. So let's look at the others here. Go ahead and work on these. And I have the so pause it a moment. Whoops, excuse me. Pause it. I'll go ahead and pause it and work on them. I've got the answers for 14 and 15 for you. Okay, let's look at these two. 14 and 15. Okay. What do we have here? I generally like to try to reduce things at first to see if I can simplify it enough that I don't have to mess with it. This one didn't really work that well to do it. I still need the calculator. Okay. So, again, need over know. So going from 1 to 2, that's getting smaller. So that I know that my scale factor is going to have to be less than 1. If I come up with 9/4, I know I did it wrong because that's going to make it bigger, because the scale factor would be bigger than 1. So let's look at this. So it's 128/288, which reduces down to 4/9. Well, that's not going to go any better than that, so just resort to the calculator. And notice, when you put it into the calculator, since 4/9 is a fraction, it'll have to have the parentheses before you raise it to the 1/3 power. Before you raise it to the 1/3 power to get the cube root. A reminder, the way you get roots other than square roots is to raise it to the fractional power. Now, for square root, there's a dedicated button because we use it so much. But for a cube root, that's the way you'll need to do it. And then here is a solution very similarly done to number 15. Okay. Okay, we've got some shapes here, and we want to know the surface area and the volume. There's at least a couple of ways to do it. Depending upon what circumstances you have and what information you're given, one might be better than the other, so you've got to kind of watch that. But here we're given a lot of information, and for some of them at least, we can do the surface area individually if we want to. So you could apply the scale, either apply the scale factor, so 3, find out what the scale factor is. 4 goes to 8. What do you do to 4 to get 8? 8/4, 2. Apply the scale factor to find out the other linear dimensions, and then calculate each one individually. That will work. Okay? Or you can calculate the one that you have all the dimensions in, and then multiply it by the square of the scale factor for the area, and the volume for the volume. Use the cube of the scale factor. So you can do it that way. Either way will work just fine. Generally speaking, it's easier to use the square and cube of the scale factor because you don't always have enough information. For example, if all you knew, well, different circumstances, but under these circumstances, for most of them, it'll work to do it either way, not all of them. Okay, so give them a try. Pause it and I'll show you the answers. Okay, here's number 19 and 21. And here's number 20 and 22, so you can see how you did. Now, on applications, give this one a try. Pause it and try to work this out. Two similar cylinders have a surface area of 54 pi square feet and 384 pi square feet. The height of each cylinder is equal to its diameter. Find the radius and height of both cylinders. Pause it and do it. Okay, here's how I worked it out. I noticed that height equals diameter, and diameter equals 2 times the radius. Then simplified the surface area formula. Put it equal to what the surface area is for each one and found out the dimensions. Okay, one more problem to challenge you. Give this one a try. Pause it. See how it goes? Here are the answers. And here endeth the lesson.